silver nanowires based sensor for detection of temperature and moisture contents in the air. First, I will briefly tell you about the plan of my presentation. First will be a brief introduction of my research, followed by synthesis and characterization of silver nanowires and cellulose paper. Then I'll be talking about fabrication of my sensor. And then the fourth one is experimental setup, which we employed to test humidity and temperature in our lab. The fifth one will be the results when this sensor was subjected to temperature and moisture in air separately. And at the end, there will be some conclusions. First one is introduction of the research. As we know that polymer is the most abundant material in nature. It is biocompatible and it has a very good mechanical properties. And other advantages is that other 0 dimension, 1 dimension, and 2 dimension nanomaterials can be easily deposited on its surface. Its other advantages are it's low cost, it is really flexible, safe to use, and recyclable. But if you can classify cellulose, it's an electrical insulator material. That means it cannot conduct electricity. Therefore, for the practical use in electronic solutions, such as sensors or some other stuff, it is very important to incorporate some of the conductive materials into the structure of the cellulose. And the remedy of this one can be one-dimension nanomaterials, which can be incorporated in the cellulose to make it electroconductive materials. The examples are silver nanowires or carbon nanotubes. Well, since I will be focusing on silver nanowires, let me give you an idea what is silver nanowire. Silver nanowire, to identify the silver nanowire, we have to first see the aspect ratio. If the aspect ratio of any nanowire is greater than 10, then that is known as silver nanowire. But if the aspect ratio is less than 10, then that nanowires becomes nanorods. So this aspect ratio basically defines what is silver nanowires and what is not silver nanowires. And question is, why did we choose silver nanowires? Because they have excellent electrical properties, optical properties, they are resistant to corrosion and have low fabrication cost. And literature survey has shown us that these above mentioned electroconductive composites can be fabricated to test to identify temperature and humidity. And why we started working on this particularly project, because there are very small number of publications present in nowadays. And in this presentation, I'll be discussing upon the preparation of silver nanowires. And once these silver nanowires has been successfully synthesized, they were combined with the cellulose to yield a fabric sensor, which is used to detect moisture and temperature in the air. Second step is synthesis of silver nanowires by polyol process. First of all, a little bit of definition what is polyol process is. Basically, polyol process is a process for synthesizing metallic nanowires by the reduction of metallic salt in a alpha diol, which can be ethylene glycol or propylene glycol. So this is a small definition of polyol. In our case, we used ethylene glycol. So I will be quickly telling about my ingredients, which were PVP, ethylene glycol, AgNO3, copper 2 chloride. These were mixed together, and the solution was heated to 150 degrees Celsius and for 70 minutes, and we got our silver nanowires. So I will briefly discuss what is the role of each ingredient is. First of all, the ethylene glycol has a dual purpose. First, it's react as a reducing agent and as well as the solvent. The role of AgNO3 is to provide seeds for the silver nanowires. And the role of PVP is to promote the anisotropic growth of the crystal. Because if you see that silver nuclei has two faces, one is 100, the second one is 111. So this PVP basically attaches itself to 100 phase, and in this way the silver ions are turned to the 111 phase, and in this way they form an anisotropic growth along the 110 direction. And coming towards the last one is copper 2 chloride. Copper 2 chloride is a mediating agent. When it dissolves into the solution, it turns into copper ions and chloride ions. The role of the chloride ions is acts as a oxygen scavenger, while copper 2 chloride has two main functions. First one is its electrostatic stabilizes the silver seeds, and second one is it prevents the accumulation of undesirably very high concentration of silver ions by making poorly soluble silver chloride salt. So this was a little bit of introduction of my polyol process. So here you can see a very good, very beautiful nanowires. The SEM images were used to characterize them, and they were shown at different magnifications. Now, the second step was to fabricate the cellulose suspension. As we know that cellulose is a long chain polymer with the glucose molecules attached to it, and the dissolution of this cellulose in deionized water is a bit challenge due to the presence of these long chain polymers. For that purpose, we used higher shear stir mixture. As you can see from the figure 4, that we purchased pulp from the market, dissolved into deionized water, and this apparatus was turned on for the 30 minutes. And figure 5 shows that we have at the end, we have a cellulose suspension. Now we have a cellulose suspension with the help of a vacuum filtration apparatus, and using drop by drop method, we were able to fabricate a Princeton cellulose paper, which has a thickness of about 0.08 millimeter. This Princeton cellulose paper will act like our substrate. So again, characterization of cellulose paper, this we did optical microscopy and SEM microscopy. Optical microscopy doesn't reveals anything, but SEM microscopy, clearly you can see that these fibrous kind of structures, and this is a clear indication or perfect indication of a cellulose material. Now, the third one is now we have to fabricate our silver nanowire cellulose composite or sensor, which by drop casting method, which was basically an ex situ method. There are two types, ex situ and in situ. Ex situ is in which the substrate and the silver nanowires were fabricated separately, and they were, after that they were joined together. I will explain you what we did. First of all, we have this schematic shows the apparatus which we used for the fabrication. This one you can see that we have already first we have Teflon filter paper. Onto the top of that we placed cellulose substrate. The cellulose substrate, I explained previously that how we fabricated it. After that, we added drop by drop suspension of silver nanowires on the top of it. And when this solid layer was dried at 30 degrees Celsius and it was compacted at 50 megapascal for 5 seconds, our sensor was ready. So next, you can see figure 11. This is what you call as fabricated silver nanowires cellulose sensor. This is how our sensors look like, a grayish kind of a color. And now we want to use it for sensing temperature. Some researchers has argued that it is good to cover your sensor with a polydimethyl silohexane, which is known as PDMS. Why? So that the effect of humidity on the resistance reading can be reduced and we can maximize the temperature sensitivity. And so here figure 12 shows us this is the arrangement what we did. We have a glass slide on the top of that. I hope everybody can see it. Then we have a grayish kind of a sensor. Then we placed copper electrodes. And then on the top of that, we have a transparent PDMS layer. So in this way, we are absolutely sure that humidity doesn't interfere in our experiments. This section 4 shows us the experimental setup which we use in our lab for temperature sensing. We have actually a double jacket glass jar in which water is circulating. We have a thermometer and a working sensor inserted in different holes. Thermometer is used to make sure that we can note the temperature of the chamber, and the working cylinder is connected to the ohm meter. And then we have a thermostat where we can control the temperature of the water from ranging from 20 degrees Celsius to 60 degrees Celsius. Coming towards part B, this will show you the experimental setup we employed for the humidity sensing. This figure 14 shows that we employed the silver nanowires-cellulose sensor for this humidity sensing. As you can see that this sensor was not coated with the PDMS. Why? Because in the case of humidity sensing, if we coat this with the PDMS layer, humidity will not interfere with the sensor and we won't get any kind of a result. So in case of the humidity sensing, we will not coat anything on this sensor. Coming towards our experimental setup, we have a chamber in which we have a thermometer which is used to make sure that the temperature remains the constant throughout the experiment. Then we have a working sensor, which one of the example is shown in figure 14. And then we have a humidity sensor, which was purchased from the market. And the reason for this is to tell us the quantity of humidity in our chamber. Then we have our boiling, we have a water available, and then we have a heater. The purpose of this one is to convert water into the vapors. When we have sufficient vapor, this valve was turned on together with the vacuum pump, and the moisture was introduced into the chamber. And when the experiment was about to be finished, thus vacuum was connected to the outlet, and this moisture was removed from the chamber. Now coming towards our results, this is our sensor PDMS coated, which I previously showed you. PDMS coated silver nanowire sensor. It has an initial resistance of 4.4 ohm at 20 degrees Celsius. So here you can see on y-axis we have resistance, on x-axis we have temperature, and heating was done from 20 to 50 degrees Celsius. From the first one heating, as you can see that if you say that, if you remember Ohm's law says that if you heat a conductive material or an ohmic material, its resistance will increase. Because why? If you increase the temperature, scattering will increase. So for the first part from 20 to 55 degrees Celsius, there is a very nice increase in resistance. This is expected. But the most important thing is when we cooled it, so the resistance came back to its original value. So in this way, we have a complete hysteresis loop in which this sensor works as a temperature sensor. Now coming towards the part B, here I have performed 5 different set of experiments, and the temperature ranges from 20 to 55 degrees Celsius. On y-axis, you can see the resistance. The main purpose of this experiment to show the repeatability. As you can see that the starting point and the finishing point and the reversibility is very good, and repeatability is also good of our sensor. Now, the third one is delta R over R naught, which is on y-axis. This represents change in resistance over original resistance, and on x-axis I have temperature. So here I have performed 5 different experiments, and the maximum change in resistance from 20 to 55 was round about 99%, which is a very good value. And most importantly, these all graphs are reversible, meaning to say that the initial value, when we heat it, the temperature resistance rises, but when we cool it, the resistance came back to its initial value in all of the 5 experiments. Now coming towards the part B. Part B, some researchers has argued that what will happen if we expose our PDMS coated silver nanowire sensor to the light source, and we try to do the same. The purpose was to check it whether what will happen. So this is just an experimental setup that what will happen if we expose a PDMS coated silver nanowire sensor. So figure 16 shows that the arrangement, it's a very simple arrangement. All you need is to fix your sensor in a petri dish. It is connected with the ohm meter. First, there is no light falling onto it. After, in figure 17, light is made to fall into it. There is a little bit of increase in resistance, and when the light was removed, it came back to its original value. So this is what you call a very simple method to test what will happen if you radiate your PDMS coated silver nanowire sensor with the IR, which is radiation method. So in this graph, again, the same sensor was used, PDMS coated silver nanowire sensor, which I discussed previously, which has a resistance of 4.4 ohm at 20 degrees Celsius. On y-axis we have resistance, on x-axis we have time, but in seconds this time. For the first 3 initial readings, you can see that the line is horizontal, so there is no change in the resistance. These readings were taking 30 seconds apart, and after that, just for 10 seconds, the light was turned on onto the radiate sample. As you can see that the resistance exponentially increases. Just for 10 seconds, I shined the light on my sensor, and after 10 seconds, the lamp was turned on, and then it gradually decreases to its initial value. So here I can say that in the previous examples, conduction was the main mechanism of heating my sensor, but here radiation is being used to heat my sensor, and as we know that radiation is much more quicker process as compared to the conduction process. And again, here we have resistance versus time. Here we have again, we radiated the sensor for just 10 seconds. We performed 5 different experiments, just show that how good we have the repeatability. And we have, in fact, have a good repeatability as well. Now coming towards the delta R over R naught versus time. This graph will tell you about the change. I mean, what will the change occurs when you shine the light for just 10 seconds. And we were, for the average of these 5 graphs, it was 34%, which is quite a good figure in our case. Now coming towards our silver nanowires-cellulose sensor, which was used to sense humidity. I showed you this sensor previously. This was a sensor which wasn't covered by the PDMS layer. This sensor has a resistance, initial resistance of 192.31 ohm at 25 degrees Celsius. So here it has 3 regions. I hope that you can see this. This is region 1 till 20 minutes, then 20 to 55 minutes. This is region 2. And after 55 to 75, 72, 70, this is what you call the region 3. I will explain it what is. So in the first region, humidity is 42%. We use this specialized equipment to measure this humidity. This is the humidity in the chamber. I mean the initial value. As you can see that there is no increase in resistance as there is a horizontal line. So after 20 minutes, what we did is we initially increased the amount of humidity. So first of all, the resistance decreases till 30 minutes, and then it becomes horizontal. The line becomes horizontal till 55 to 56 minutes. So what is happening here? Because if you consider the formula R is equal to PL over A, R is basically the resistance, P is the resistivity, A is the area of cross-sectional area. When you expose your sensor to the humidity, your sensor will since it is made of the cellulose, which is in fact a very good humidity absorber, it will absorb the humidity, and the cross-sectional area will increase. So that is the reason, as we increase the humidity level, this cross-sectional area becomes swell, and we have a resistance decreases. But there is an extent to which my sensor can swell. And this is also evident from this horizontal line. The humidity level is 95%, and this is the point which says that this is the maximum extent to which my sensor has swollen. Further, my sensor will not swell, and after that, we decided to remove the humidity. As you can see that there is for a few minutes, the resistance remains the constant, and then it starts to increase till now. Again, this is perfectly concept. When the humidity is removed, the swollen sensor becomes deswelled, and this cross-sectional area becomes lesser, and the resistance increases. Until now, we have reached till this point. This is very important, and this is a very interesting point. As you can see that for few minutes, for 4, 5 minutes or 6 minutes, the line remains constant. This is because the evaporation is being done from the surface of the sensor. Once all the moisture has been evaporated from the surface of the sensor, this readings continues to increase. And now this reason for the continuation increase is because now the moisture which has been absorbed which is present within the matrix of the sensor, it is now being removed, and until we reaches our value which coincides with the initial value. So here we can say that initial value, final value are the same. Initial value and the final humidity level is also the same. Again, delta R over R naught, it goes a very beautiful change. There is a change, there is a decrease in resistance till 65% when you expose it to humidity from 42 to 95%. And now coming towards the third part. In the third part, we did 3 different experiments with the humidity level. You can see that 75%, 85%, and 95%. And all things, if you see that there is one thing common in which that maximum change is almost the same, which is almost the 65%. So here I will propose an idea that there is a maximum limit to which my sensor can swell, and this is defined by a critical value of moisture. For example, let's say the critical value of moisture is 72 or 73%. Below this critical value of moisture, swelling of my sensor is directly proportional to the moisture content. That means resistance decreases with the increase of moisture. At this critical value, for example, let's say it is 72% or 73%, maximum swelling has been occurred, or I can say that this is the maximum extent to which my sensor has swollen. And if you cross the critical value, there is no change in the swelling. There is no change in the resistance. The line becomes horizontal. That means that sensor cannot swell. So in this way, we can propose that I can say that in 3 of the cases, we have exceeded the critical value of humidity. Maybe in our case, critical humidity was 72%, 73%, but we need more experiments to confirm that thing. But we are sure that we have gone above the critical humidity level. That's why in 3 of the cases, 75%, 85%, and 95%, the change is the maximum change is approximately the same, which is about 65%. And in the conclusion, I can say that we successfully synthesized silver nanowires and successfully fabricated electrocomposite paper containing cellulose by drop casting method. And our preliminary research shows that when the temperature was increased to 20 to 55, there was an average increase in resistance was 99%. Obviously, this resistance was reversible. And in the second part, when the lamp was turned on just for 10 seconds, the average increase in resistance was 34%. Again, reversible resistance. This is reversible resistance is very important. And at the end, when the relative humidity was increased from 42 to 95%, there was an average decrease of about 65% was seen. Thank you so much. That will be end from my side.
Thank you very much.
On behalf of the organizers, we would like to ask the Polish participants to turn on their cameras so we can take a photo of all the participants.
Y estaríamos listos para tomar la fotografía, señora Mayra.
Rick Delgadillo, ¿podría encender su cámara también? Es expositor. Bueno, I will take a picture. Please let me one more, please.